Okay, so now we want to look at how we can use a multiplexer. And we have to remember how the multiplexer works. So we have to look at the data sheet for the multiplexer. So one thing I did not show on this that I should have shown is that, of course, you need to connect ground to ground on all of these and VCC to high voltage. So on each of these chips, the pin 14 needs to be connected. Pin 14 needs to be connected to high voltage, and ground needs to be connected to ground. So make sure you do that, even though I didn't show it.
For the MER, it's coming from one Y, right?
It is coming from one Y, yes, on the OR gate. Okay, so let's take a look at the connection diagram for our multiplexer. And this one is different. I don't think that you used it in 2741. So it has, so this part's important. It has select inputs S0 through S2. It has an enable active low input, that's important. It has multiplexer inputs, and it has a multiplexer output. Then it also has the complementary multiplexer output. So let's remind ourselves of what the multiplexer does. So schematically first. So I have a multiplexer. And I have 3 inputs. And normally we just draw it with one output. We can draw it with one output and its complement. The way this works is based on what your select inputs are. So if my S2, S1, S0 is 0, 1, 0, that's binary for 2. And that means that whatever input I have coming into 2, that's going to be what comes out at Z. So the input that's going into this number right here is going to be what comes out at Z based on the select input. So for example, let's say I had S2, S1, S0 equal to 1, 0, 1, and I had the following numbers, or I had 1 is high voltage and 0 is low voltage, so you can always just use those if you need to. Okay, so let's say I had these, and my select inputs are S2, S1, S0, and I'm saying that that is 1, 0, 1. So what is my output in this case going to be? What would Z equal and what would Z bar be? Okay, so first, what binary number does 1, 0, 1 equal to? 5. Okay, so then we find 5. We look at the input for 5, it's 0. So that tells us Z would be 0. And Z bar would be 1, just the opposite of that. Yeah?
Is every multiplexer set up with each input to have 1, 0, 1, 0 alternator?
No, that was just, I didn't mean to do it like that. You connect these.
Okay.
You put what you want to here, so you would put like X1 here, and not X1 here. and we're going to talk about how we figure out how to do that. What do we actually want on our multiplexer?
Okay.
Yeah, I just put those on there so to make sure that everybody knew how it worked. Does everybody see now how it does work? Okay, so now let's go back and look at our truth table. It would be real handy if we only had to do the first 7 Mersenne numbers. I mean, if we only had 3 digits. Because if we only had 3 digits, then all we would have to do would be, if we just had to get the 1, 3, and 7, we could put a 1 here, and a 1 here, and a 1 here, and a 0 everywhere else. And we could just have our inputs x2, x1, x0 if we only had 3 bits, but we don't, we have 4 bits. So we can't do that. So we have to figure out something else. And I think the directions say we can only use one multiplexer.
It says to use one multiplexer,
But-
input multiplexer, and other chips as needed.
Okay, all right. So let's take a look at our truth table. And let's take a look at where our 1s are. So our 1s are here, 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 and here. And let's see if there's any trick that we can use that will let us use our multiplexer in a very efficient way to get the output that we want. So first of all, let's see, we know that x0 is 1 for all of them, right? All of these that I have circled. X0 is 1. All right, now, let's see. If we just use these first 3 digits. Okay. So just look at x3, x2, and x1. Then I have 0, 0, 0. And I have for this first one. And I have 0, 0, 1 for the second one. And I have 0, 1, 1 for the third one. And I have 1, 1, 1 for the fourth one. So if
Is that supposed to be x3?
it is supposed to be x3. So if x3, x2, x1 equals one of these, and x0 equals 1, does that catch everything? Now look at it and see. Now tell me. This is first I've thought of it. So
You say?
yeah. So I'm saying that this is what I am proposing. So I am proposing that we use our multiplexer like this, and our inputs are going to be x3, x2, x1, and I said we had 0, 0, 0. And I'm saying if we had one, 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 0, 0, 0, 0, and I AND this output with x0, that goes to MER, and that gets my answer. I'm proposing that. I'm not saying for sure. You keep shaking your head, so I'm curious as to what you see that's wrong with it. Because I'm actually not trying to be tricky. I'm not trying to get y'all to find what's wrong with it.
That, I don't know if I'm right, but you're asking that if an x0 is 1, the MER is 1.
No, if x0 is 1 and x3, x2, x1 are one of those things there. So it has, both of those have to be true.
And this is because you can only have 3 inputs.
I only have 3 inputs and I can only use one multiplexer, so I can't chain them together to make 2 multiplexers. Okay, but there's going to be a twist to this. Now let's take a look at what the twist is. The twist is that this is, need to look at our truth table. It has an enable low, and its output, let's see, the output is high, let's see. So first of all, the enable needs to be low, so that's important. So you will have pin 7 on your chip will have to be connected to ground as well as pin 8. Because if you don't do that, it is not going to work.
So enable just activates the chip.
The chip. And the reason why you have it is because you can chain them together to make different chips and have them enabled or not enabled. Okay, so we have that. Now let's take a look if input needs to be high or low. So if I want 0, 0, 0, okay, so take a look at how this is working. Look at this truth table. And it's not the way you would think. It has your select inputs. If your select inputs are all low, so that'd be 0, 0, 0, then I0 is 0, then the output is high. And if the input is high, then the oh no, that's Z bar. Okay, good, never mind. Okay, good, all right, so it works the way we expect it to. Okay.
So I0 is your...
That's our input. This is our input. So these are what I have labeled as 0, 1, 2, 3, 4, 5. And this is, so if we have, we would want 0, 0, 0 was one that we had, right? So we would want 1 to be connected to it. So let's set it up. Let's set it up and see how we would have it set up. So we would have our chip is going to look like yes.
Just to make sure you did say connect the enable and ground both to ground.
Yes,
What was the reason for connecting the E to ground again?
because you have to look at the data sheet, and the data sheet tells us E enable active low input. And so that's how we knew. And when we get to the decoder, it's crazy. Okay, so we know we need to have this connected to high voltage. And we need to have E and Z connected to ground. And we decided that we had, let's see, we were using X3, X2, and X1 as our select. So that's going to be X3 goes to S2, X2 goes to S1, and X1 goes to S0. And we had 0, 0, 0, 0, 0, 1, 0, 1, 1, and 1, 1, 1. So we wanted those values, which are 0, 1, 3, and 7, to be high. So 0, 1, 3, and 7 will be high, and all the others will be low. Hopefully those numbers, hold on, let me make sure those numbers match up with, look at the data sheet. I0 goes with 0, 0, 0, I1 goes with 0, 0, 1. I2 goes with 0, 1, 0. Yes, good. Okay, they do. And then we would need to take our output, which is either 5 or 6. Let's see. 5. 5 is Z and 6 is Z bar. So we would take our output, and AND it with X1. And that would be MER. So that's one way to do it. It's not the only way to do it. There are other ways of doing it, for sure. It's not the only way.
Can you go up a little bit?
And you will need to double check all of this with the data sheet, make sure I have it drawn right. Yeah.
When you connect pins 1 through 4, 16 and 12 to high voltage, is that like the VCC plus 5 volts that you want us to?
Yes.
Could we connect it to X of 0? Does that also be on?
That would not work because that would not work because it would get you, it would not would it get you this value? So let's say, okay, so if you had, and you connected 7 to X1, in fact x1.
High output voltage.
Yeah, that would work. Yep.
Is I4, 5, and 6 being connected to X1? And if so, why?
I4, 5, and 6, I do not mean for them to be connected to X1. I meant for them to be connected to ground. My problem was with my colors. Those should be connected to ground. Thank you. Thanks for asking.
How come those are wrong?
Because they were always low. They were not any of these values right here. Yes.
Is I2 supposed to be connected to ground, or you just let it?
I2 is supposed to be connected to ground, right?
And do you have to connect it to ground, or can you just have it?
I think it ends up not working if you don't connect it to ground, but I'm not 100%. So who asked that question? Yeah, so I mean, I'd feel free to try it and see. I think it ends up not working if you don't connect it to ground.
And what is number 5? Number 5 and
Number 5 is connected to an AND gate that is connected to X1, X0, and the output is your MER.
Is 0 a Merson number?
Is 0 a Merson number? No. Why not? Could it be 2? Because I think it depends on n. N has to be greater than or equal to 1.
Okay, I think you have it labeled as a Merson number.
Well, but 0001 is.
But what about 0, 0, 0?
Well, that would end up not getting detected because X0 would be 0. See, these numbers are the first 3 bits of the Merson number.
Wait, so we need 2, right?
2 what's?
For these 2 chips. Would you need one to AND it, or would you?
You'll need an AND chip. You just need an AND chip.
You can't have 2 on this line.
You can only have one multiplexer, but you just need one in the AND and the AND.
So, regarding the 0137, how did you put it again? I just went from.
Went from the truth table, and when I looked at the truth table,
Well, how did you plug it in the multiplexer? When we went.
how did I plug it into the multiplexer?
Yeah, that's.
I did. I figured out. Well, first I figured out that these were the binary numbers for 0137, which these are not the Merson numbers. These are the first 3 bits of the Merson numbers 001, 0011, 0111, and 1111. Those are the first 3 bits of those. But then I said, what are these numbers as binary numbers? They're 0137 because I'm feeding the first 3 bits of the number into the select bits, so I'm getting their binary values, and then I'm setting those to high, to 1.
Okay, so the one.
So 1, 0, 1, 3, and 7 are all set to 1, and the others are set to 0.
Okay, cool.
Is this all for the lab?
Nope. Unfortunately, there's still the hardest part. Yes.
I think you just explained, but how did we get the 0137 from the truth table again?
I didn't just explain, I was about to. So what I did was, knowing that I could only use one multiplexer that has 3 inputs, I looked at said, well, what if I select off the last X0 and I just look at X3, X2, and X1? What values on there correspond to the values that I need to get. So this is 1, that was 0, 0, 0. This was 0, 0, 1, 0, 1, 1, and 1, 1, 1. Those were the values I needed to get. But there's a problem because 0, 0, 0 also fits that model, but it's not one that I want to detect. But I noticed that all of the ones that I want to detect also have a 1 for x0. So I detect 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, and 1, 1, 1. I detect that, and that's half of the detection, and then I AND it with x0, which then will tell me if those are both true, then I have a Mersenne number.
Where can we find the recordings?
It'll be on the Moodle page for 2742 under Fall 2025 SI Resources. I just made that folder. So
What was the posting when you were done?
it'll be posted later this evening. It has to render and process, but it'll be posted later this evening. Okay. Other questions before we look at the decoder? Okay, because you, yeah.
The alternative way that I did it
Sure.
before and before it's gone. Do you want me to just show it to you, or?
Yeah, just show it to me quickly. Because there are definitely different ways of doing it. Are you using 2 multiplexers?
Just one. The other one's a not gate.
That's a not gate. I would have to look at it more carefully, but if your logic works, like if you found a way, like you have x0, x1 and x2, and y is not of x3. I can't do it in my head. I have to write it out and see. But I think it is certainly possible that it works. So there's nothing that I see in there to say, oh no, that's not going to work. If your logic is right, it definitely could work. All right. So now we're going to talk about decoder. And the way a decoder works. Okay, first of all, the thing to be aware of is that the decoder that y'all have is active low. Let me first pretend like we had a decoder that had 16 inputs. Okay, so let's pretend we had a decoder that had 16 inputs. Or 16 outputs. 16 outputs. 4 inputs, 16 outputs.
She's asking, do we only need to use 2 versions?
You only have to do 2 versions in the lab. You have to have all 3 in the pre-lab. Okay, so this is a decoder that we don't have. But if we did have, it would be great because we'd only have to use 1 of them. because the way the decoder works is that it will output a high signal at the output corresponding to the binary number that's being input. So for example, if I put in a 1010, that is the binary number 10, and so it would output a low here and high everywhere else because it's active low. So okay, so it just outputs a low signal on the binary number that you have. So if we had a decoder that had 15 outputs on it, all we would have to do would be to take the outputs for 1, 3, 7, and 15, and we would want, what gate do we want for these? If any of them would be a NAND.
What was the decoder that we had in the lab? You said again?
It was a 138, 74 138. Yeah, we would need a NAND, a 4-input NAND. Why a 4-input NAND? Because it's active low. So if this was active high, we would just have an OR gate here. We would say if any of these was high, we're good to go, because those are the ones we're trying to detect. But it's active low, and so we want to know if any of them is low. And to get that, you would use a NAND.
You said we had an 8-bit decoder, so can't we just use x0, 1, and 2 and ignore x3?
And then what would you do with the...
You ignore it because if it's a for 7, if it's 7 and if we know that it's 0, 1, 1, 1 or 1, 1, 1, 1, then the last end does not matter. X to 3 does not matter.
So if you have...
If it's at least 7, then it's... I mean, if it is 7.
yeah, you could do that. But that doesn't... No, you can't do that, because that would get you a positive for this. That would get you that this was a Mersenne number when it's not, if you just ignore x3. Okay, so what we have to do is we have to string 2 of these together. And the way we do it is as follows. So you'll notice on the data sheet for this one that you have to have, in order for it to be enabled, E1 and E2 have to be low and E3 has to be high in order for it to be enabled. So E1 and E2 have to be low and E3 has to be high in order to be enabled. And your inputs are A0, A1, A2. And are those also reverse of what we want? No. Okay, so what did I just say? E1, E2 low, E3 high.
So we need 2?
Yep. So what you do is you put So I put X3 as the input to E1 on the first chip. So in order to be enabled, E1, E2, E3, E1 needs to be low, E2 needs to be low, E3 needs to be high. If X3 equals 0, which one of these is enabled? And is the right one disabled?
Yes.
And if X3 is equal to 1, this one is disabled, and this one is enabled. That allows you to use this as if it were 15, had 15 outputs. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then you have X0, X1, X2 as your inputs into A0, A1, A2 on both of them. And then you would just NAND together the outputs that you need. So 1, 3, 7, and 15. You just take those outputs, find a 4-input NAND gate. And that should work. Yep.
What is the name of the chip for the DMUX?
It is a 74-138. And unfortunately, that's going to be where I have to stop here. I have a few minutes for questions, and that's hopefully enough to give you an idea as to how to do it. Or at least to get you thinking about it. Let me see if I have anything else that I'm supposed to remind you of. Common pitfalls, the fact that it's active low, so we're not ORing together the outputs.
So we actually can't use any of this. Like, can we?
Yeah,
Oh, we can?
yeah.
Oh, okay. I was confused.
What do you mean?
I thought you meant like we had to like you were just showing us what to do. And
Oh
then
no,
we start all of
I
it.
always pretend like I'm not going to show y'all exactly what to do, and then I show you exactly what to do. I always have these grand ideas of I'm going to just give them, hints, and then I end up doing everything.